Hello everyone. We want to start a new topic which is related to multiphase flow, and it's called capillary pressure. It's sort of related to interfacial tension and topics that we have discussed previously, and we want to introduce it here. You might have heard it in your physics class. Alright, so let's start. Remember we talked about wettability. Wettability, we defined the adhesion tension, AT, right? And AT was called adhesion tension, the difference between the interfacial tension of oil and solid. So if you have water and then you have surrounding oil, then there is interfacial tension of oil and solid, interfacial tension of water and solid, and then there is this interfacial tension between water and oil. So if you write the force balance on the x direction, you will see that sigma OS minus sigma WS is going to be sigma OW cosine theta, which is going to be on the x-axis, right? And we called the difference between oil and solid and water solid interfacial tensions adhesion tension. And that is equal to sigma OW cosine theta. Theta was called contact angle. And remember, we always measure theta toward the denser liquid. It's always through the denser liquid. So water is denser than oil. So in this case, this is your theta. So that's called contact angle. So we have this definition of as wettability, and wettability was when your contact angle is less than 90. Then the water wets your surface. If your contact angle is more than 90, usually the water, if you have a water oil system, water is the non-wetting phase. Now it has some implications, and especially we talked about this previously. One of the most important implications that we have here is that if you have I think we have discussed this as well, but if you have a tube, a narrow tube, I think we discussed in a horizontal tube previously. So consider that you have a horizontal tube and you put, this is a narrow tube, and you put it in contact with water, and assume that this tube is water wet. So it means that it likes water more than other fluids. So if you put this in contact with water, then the water starts to wet the surface, right? So let me see if I can change the color. All right, so the water wets the surface, right? Start to wet the surface from all areas of the solid, or in this case this tube, and it starts to further wet the surface, and the water starts to fill this tube eventually, because if these two walls are very close to each other, then the water sits on the surface, create a film, and these two films together fills the tube, right? So eventually you will have a process which is called imbibition, and imbibition means that the wetting phase displaces the non-wetting phase. In this case, air which was already inside the tube was the non-wetting phase. Now if you have a long tube, if there is no force to prevent that fluid from, or prevent water from entering this tube, this water will fill all the way until it fills the whole capillary tube. Okay, now let's consider a system which is vertical, and then you have, let's say, a bucket of water here, and you put this, insert this capillary tube inside this bucket of water. Okay, what happens? Now, again, this tube is a water width. Let's assume that. And then you have this water entering this system, right? Again, wets the surface, and wets the surface, wets the surface, wets the surface, continuously wets the surface until it stops. Now, what is the difference between this vertical tube and this horizontal tube? The difference is that in a horizontal tube, if there is no friction or other forces that prevent water from continuously wetting the surface of the tube, in vertical tube, however, you have this gravitation or the weight of the water that is being added to that tube against the net adhesive forces. So there are two forces going on here. One is gravitational force of the water. One is the net adhesive force that tries to fill this tube up, right? So it will stop at the point that this gravitational force is equal to the net adhesive force of the water to the surface of the tube. Okay, now this is what happens, right? So now we define, so here is air, right? Here is water. And it creates at the top, it creates a surface, right? Like maybe like this. Because water is the wetting phase, right? It will try to be to adhere to the surface. Here is air, here is water, and then we have air is the non-wetting phase, right? Water is the wetting phase. Now, we define capillary pressure as the pressure which is required to push the non-wetting phase into the tube in order to remove the wetting phase from the tube. How much pressure do we need? Okay, again, the pressure that is required to push the non-wetting phase, in this case air, to displace the water from the tube completely. Okay, and that is equal to the pressure difference at the surface of interface of air and water. Okay, so if you look at this picture, you see that there is water here, there is air here, there is a water pressure exactly at the surface of the water and air interface, and there is this air pressure that is applied from the top, right, to the surface. So these two pressures are different. They are not the same because of this adhesion tension. So the non-wetting pressure, the pressure inside the non-wetting phase, which is air at the interface, is not equal to the pressure of the wetting phase exactly at the boundary. So there is a difference, and that difference is called capillary pressure. Okay, so let's derive the capillary pressure equation for a simple case of water and air. Okay, how do we derive this equation? So we define this as general equation of capillary pressure, right? But how do we really find an equation which relates the capillary pressure to measurable properties, right? So let's look at the interface again, right? What we need to do is to write a force balance. So there is a sigma, which is basically the sigma interfacial tension of water and the surface of this tube, right? Because that's what causes water to raise inside the tube, right? So if you decompose this into y direction, this is going to be sigma cosine theta, right? And how many of these sigma cosine thetas you have? You have all these sigma cosine thetas around the perimeter of the interface, right? So you have 2 pi r of sigma cosine theta applied upward, right? What other force do we have? We have pressure, which is pressure of non-bending phase, multiplied by what? If we want to make it force, we should multiply it by cross-sectional area, which is pi r squared. And then we have the pressure of bending phase multiplied by pi r squared, right? Now, if we write the force balance, the pressure of the non-bending phase is downward, this is upward. So what we get is pressure of bending phase multiplied by pi r squared plus 2 pi r sigma cosine theta is equal to pressure of non-bending phase multiplied by pi r squared. And pi can cancel out from each side of the equation, right? And if we take the p of the bending phase to the other side, we get 2 pi r cosine theta, 2 pi r sigma cosine theta, and that sigma is between water and the surface, right? Sorry, between water and air. And this is equal to P non-wetting minus P wetting multiplied by pi r squared, right? Just factor out pi r squared. Now, by definition, P non-wetting minus P wetting is capillary pressure, so that's PC. Pi can cancel out. One of the r's will cancel out from each side, so PC is equal to 2 sigma cosine theta divided by r, and r is the radius of the capillary pressure, okay, which is this equation here. So for a capillary tube, the capillary pressure can be calculated if you know the interfacial tension of these two phases, between these two phases, the contact angle at the surface of the solid, and the radius of the capillary tube. So the narrower the tube is, the higher the capillary pressure is based on this equation, right? So you need more pressure in order to push the air to displace the water completely from the capillary tube if you have a narrower tube, right? So the narrower the tube, the higher the capillary pressure will be. Of course, the larger the tube in terms of diameter, you need less pressure until some point that you don't have any capillary pressure if your radius is large enough compared to your sigma value, right? So if your radius is much larger than your interfacial tension, then the capillary pressure is almost zero, and you can see the height is going down, 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 until if you have a large bucket, then the surface is completely flat, right? So there is no capillary pressure in that case. Alright, so in the next video, I'm going to continue the topic of capillary pressure.